The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so yesterday we went through quantum mechanics and discussed the solutions of the Schrodinger equation. We started with a one-dimensional problem, is a quantum well. Two-dimensional problem, now we call it a quantum wire. And then say you can extend that to a 3D. That's easy. And then I gave a hand-waving solution for the harmonic oscillator. I gave you the result, but I said I have my way to solve it. And then I don't have a way to solve rigid rotor my way. Maybe you can find it. And the electronic, we give the results, right? And in fact, I said that you can also do electronic. I know that you can do and find out. So for different problems, the difference is really the potential in the Schrodinger equation plus a boundary condition. That determine why some of the solution, like quantum well, the energy level is proportional to n squared. The harmonic oscillator is proportional to n. And the electrons in atoms is 1 over n squared. Those are because of the constraint of different shapes of the potentials. And why we discussed 1D and 2D problems. The important message we get is if it's a 1 degree freedom, one-dimensional problem, we have one quantum number. And two-dimensional problem, we have two quantum numbers. And three-dimensional problem, like atoms, we have three quantum numbers. And of course, later on, we add the spin because that's not something you can get from the Schrodinger equation. And then say quantum state is, say, each set of unique combinations of those quantum numbers give you one quantum state. The problem is sometimes different quantum states have the same energy. So when we count, we say when different states have same energy, those states are degenerate. And we can count the degeneracy of those states. And those are later on important because essentially when we do the count the number of particles like we did in first chapter, first two lectures, we need those counting. We need to do the counting correctly. So degeneracy is later on going to be evolved into a density of states. And spin is something we cannot easily say we cannot get from Schrodinger equation. You have to go to relativistic. And but for electrons, it's half spin, positive minus 1/2, and those are fermions. And photons, molecules, the uncharged, are bosons. And for fermions, the Pauli exclusion principle says each quantum state can have maximum of one particle. So if it's a fermion particle, each quantum state can only have one to the maximum. You can have empty, right? Empty or one. So that's easy to count. And for boson, each quantum state can have infinite number. So this is when you think about this harmonic oscillator, the energy is n times h bar, and say h bar mu, so h bar omega, right? The n could be 0, 1, 2, 3. Those are say many say n numbers. So this is what we talked about, and in those examples, the wave function are confined, right? When I have a quantum well or quantum wire, the wave function is in the space that I'm discussing. When I have an atom, the wave function is limited to surrounding the nuclei, right? So oscillator, that's the local, right? So this is what we discussed so far. And today, where I'm going is I'm going to put the atoms together, right, to have solid, to have crystals. And how, say, this putting them together, how they will change the energy states in what we discussed. So what we're going to discuss today is the energy levels in solids. Particularly, I'll focus on electron today. And hopefully by the end of the lecture, you will appreciate why we have metals, we have semiconductors, we have insulators, right? These are all daily encounters, but until you have this quantum picture, you really can't explain. And so we have metals, semiconductors, and insulators, right? And one very useful mathematical theorem that I introduced today is the so-called block theorem. It's a This is a theorem that applies when the potential is periodic. So when I deal with crystals, the atoms are arranged in periodic fashion. And because of this periodicity, I can solve the problem, even though the crystal is ideal crystal is infinite, periodic arrangement of atoms. And because of periodicity, I can fold all the problems into one period. And that's very beautiful. Okay, and in fact, the block theorem is valid for all waves, all periodic structure, say when you have wave propagated inside. And when you deal with the heat conduction equation, or when you deal with the transport, when there is temperature gradient, this is a lot longer valid, or diffusion, right? And then for several years, I've been trying to say what's a corresponding theorem in the diffusion regime. And because when I do a composite and those kind of problems, transport problems, a composite has many different materials. I think about 2, A and B, right? My simplest is I take a unit cell. Can I solve that unit cell problem and yet to be representative that I'm dealing with the whole structure, right? So those are the things that good question to ask. And so let's start. We say we're dealing with electrons, right? And in the last lecture, yesterday, we deal with the electron when we say our model is I have an atom, and I have electron, right? If you recall, at the end, we show the wave functions. We showed in computer the different n equals 1, say, for example, the wave function when 3 quantum number, 1, 0, 0, and of course, electron spin, right? That's n equals 1, L equals 0, M equals 0, right? Those wave functions is the lowest energy level spherical wave function that shares there, okay, right? And so this is, of course, you can have higher other, say, wave functions combinations. And now, my question is, what about, this is a simple, you think about hydrogen atom. What happens to a hydrogen molecule when I put 2 atoms close together, right? So in the case of single atom, I have this n equals 1 energy level, and n equals 2, right? In the hydrogen model, we have the energy is degenerate, is minus 13.6 electron volts over n squared, right? 13.6 electron volts is also another energy unit. Sometimes people use is Rydberg, 1 Rydberg. Okay, and so this is of course we say degenerate because I have a 3 quantum number NLM and plus the spin quantum number, right? So if I have one hydrogen atom, say atom, the electron sits in the lowest energy level. And now if I put 2 hydrogen atoms, so I have 1 hydrogen atom, those are the electron wave function, right? If you recall, it's spherical, right? And I have another, so this is 1 hydrogen atom, and I have another hydrogen atom, an electron is spherical wave function. Now, when they interact with each other to form molecule, the electron wave functions start to overlap, and the Pauli exclusion principle kicks in. You can't do that. Now the 2 electron, right? Each hydrogen has 1 electron. The 2 electron cannot have the same wave function because say the Pauli exclusion in 1 quantum state doesn't take 2 electrons. So what happens? And they will have to modify that quantum state and split it. And the splitting gives you, if you go to solve the say wave function, you'll say, okay, this is the atom, say hydrogen atom. In one case, its wave function is more, each one separated from each other, and the other case, this wave function is the probability of finding electrons, remember, right? If you do complex conjugate. And the other case, you have the wave function more surroundingly, right? This is a sigma bonds, covalent bonding, and that's the strongest, the lower energy. This is the anti-bonds, sigma star, higher energy. So what happens is this energy, single energy for an atom now, because the Pauli exclusion principle, when they have 2 electrons for the identical states, they can't do it, so they split into 2 small with a separation of the 2 energy levels, right? So the states split into from 1 to 2. Okay, so this is the higher energy level, this is the lower energy level. Now with this, I can ask the question, what if I put the hydrogen atom into a chain, not just a molecule, right? And if I have n hydrogen atom, what's going to happen, right? They are capital N, not that it's small n. Right? If I have capital N atoms, what's going to happen to n equals 1? Right, it's split into n energy levels, right? And similarly, n equals 2. So basically, if I have, you will have energy split into each of those will split into energy level, right? And now, of course, that depends on here is how large is this spread, and these two could actually overlap, right? This is originally 13.6 EV divided by n squared, so this is a few EV, right? If this splitting start to overlap with each other, you have almost continuous, right? Those are relatively small level separation between energy levels, right? So this gives us the precursor to what happens if I have, say, one-dimensional atomic chain. So crystals. Let's take a bigger, right? So my simplest picture is a one-dimensional arrangement. Crystals are the periodic arrangement of atoms. So I have periodic arrangement of atoms. And the potential is periodic. So around each atom, the electron, recall the Coulomb potential is negative C over R, right? So here, when I close to atom, the potential is lowest, and in between is higher potential. So I have periodic potential field to the charge, right? So now we want to find out. We see we already got some idea. This is what's going to happen. The energy is going to split, and we want to find the split energy levels. Okay? And we're going to solve the Schrodinger equation for that. And in fact, there are really this problem, you can look at it from 3 pictures. Let me explain briefly. The first picture I already said the atomic orbital overlapping. So if I simplify this potential, right, I give a square rather than what I draw 1 over R. Okay, so here I have lowest. So this is the periodic. That's another way I model those potential. The real atom is never just this square. It's like I say, this very much depend on the energy level depends on the potential shape. And of course, if I do a square, then I have the picture. I have quantum wells, right? If it's an infinite potential, I have the standing wave for electrons, quantum wells. But say this is normally not infinite, right? There's certain height, so it turns out from wave mechanics perspective, say later on when we do chapter 5, you'll see the wave can tunnel from one side to the other. So they start talking, overlapping, and then quantum mechanics policy, explosion principle say you can't overlap the quantum state. So they will split this. This was split into again the ones that we describe here when atom orbitals start to overlap. And these are the ones. This is the one picture. I say, okay, we start thinking about the quantum well picture, right? And the other picture is I have free electron moving in space. Okay, and when free electron moving in space. And when it start to see, so those are the electrons with higher energy. They start to see a bumpy potential underneath it, periodic bumpy potential underneath it, right? And in that case, what happens, some of you may have the experience using the interference filter in your lab, optical interference filters in your lab, right? So that's an optical wave comes in, and interference filter is typically a periodic layer deposition with different refractive index. So what happens is then some of the wave will transmit through, others reflect back. That's why I say you can get lateral lines in interference filter. So the reflected back ones are the ones that do not exist. So those are the ones the wave cannot exist. So this is the gap here in the solid. Okay, this is what this leads to is a semiconductor with a band gap. Okay, and so you have this 2 picture, and the 3rd picture is what I'm going to actually solve. I solve the Schrodinger equation, and then the solution tells us what are the energy level, and all this will converge into what we said already. So here I have the, this is the periodicity, T, right? And let's say under my picture here, I'm going to take a 1 unit cell, 1 period, and trying to solve the Schrodinger equation in that period. Right? I can take any period. So I put my coordinate here is my origin of the coordinate. And this is 0, and this is the x direction. And here is A, and here is, let's say, because this is on the other side, is minus B. Okay? And from minus B to A, that's add together is my period T. Right? And I want to solve the Schrodinger equation in this 1 period. But I want to represent the whole structure is periodic. My potential is repeating from every minus B to A, right? So here the potential is at the bottom. Let's say the potential is 0. Here the potential is U0, right? So for an electron, in one region there's 0 potential, the other region is U0 potential. And now I want to say, what are the allowable energy levels of this electron in such a periodic potential? This is my question. Okay? So I will have to write down the Schrodinger equation for each region. Between 0 and A, the potential is 0. And between negative P to 0 is potential U0. So I have 2 different regions. One is and minus E psi equals 0. Right? And the other is, so this is between, for x between A and 0. The other is for x between 0 and negative B. And in that region, my Schrodinger equation is 2m d psi dx squared plus U0 minus E psi equals 0. So I have 2 regions. And of course, I need the boundary conditions. And at the end, what I'm curious is still what are the energies of the electron. Right? So we solved this type of problem in the last lecture. And here is, say, a finite height. Before we say potential is infinite, so in that region, the wave function is 0. But now I have finite U0, so my wave function is not 0 in this region. So I'm going to solve this. The first one, let's write the equation. Yesterday, I was using small k. But today, let me switch to capital K. Capital K is k squared wave function. So this is for this region for between 0 and A. Okay? And k squared is same notation I want to find if I put this together is 2me divided by h bar squared. That's k squared. All right? And I'm going to solve this. You know the solution already. So in this region, 0a, my wave function as function of x is a exponential minus I k, capital K, x, plus b exponential plus I, capital K, x. So this is one region that I'm interested in, 0 to A. The other region is from minus B to 0. Right? If you look at the equation there, is plus U0 minus E. Right? Of course, you can write it also into negative. You can do the same. But let me, if my Q squared equals 2m U0 minus E divided by H squared. So K squared is 2m E H squared. Now E is negative, so my solution, my root then is plus minus Q. Is not a plus minus IK, right? That's the characteristic equation for this one. And then solution then is say exponential minus QX plus D exponential plus QX, right? You can write into I if you reverse E and U. Your choice. Doesn't matter. At the end, as long as you're consistent after your math, you're fine. So what I want to find out is actually E. This is my target. What are the energy of the electron, right? It's an eigenvalue problem. Okay. So I need to look at the solution and give a boundary condition to the problem so that I can solve for, eventually I want to solve for E, right? So what are my boundary? Between minus B to A, the interface here between the two regions, x equals 0. There's a boundary, right? At this location, the wave function itself has to be continuous. And also, I tell you the derivative of wave function has to be continuous. Okay, and I'm not going to demonstrate to prove it, but say basically, if you say your particle flux expression that we had before, if you require the particle flux has to be continuous, if your wave function is continuous, your derivative also has to be continuous. So, so my either x equals 0. What I have is this wave function is continuous, right? So on the two sides, the wave function is continuous. What I have A plus B equals C plus D. Now you say I will need 4 boundary conditions, right? And either say first order derivative has to be continuous. So what I have is IK and mass A plus B. That's the derivative at the x equals to 0 equals Q minus C plus D. Those are the continuity at x equal to 0. Now I have 2 boundary conditions. I need 2 more, right? So this is where I mentioned at the beginning the Bloch theorem started kicking. Why? The problem is if I just write this 2 boundary condition, it's just a single interface. It bears nothing to do with the periodicity of the crystal. Now, if you go back to the potential, the U potential is a function of x. Of course, in the problem we have here is a step function. We use a square, so it's a step function, right? In general, any arbitrary function. But it's a periodic, so U x equals to U x plus t. Right? That's the periodicity. So if you use this periodicity and you go to the Schrodinger equation and you ask what does this periodicity bring you to the solution? What's the requirement for your solution? And mathematically, the Bloch theorem, Bloch proved that because of this potential periodicity, my wave function, so due to periodicity, the wave function has to be after, so wave function x plus t later, so, right? So 1 period later, the same location is related to the wave function of x, previous period, same location, by I k times t. So this k is small k. And that's the block theorem here. And in fact, say you can write this in more general term. And so here, so this is a 1D, and there are 3D version, which we could comment later on. And this small k is a wave vector that we'll discuss more later on. That's why I'm using capital K for the solution and to distinguish from the small k wave vector. Okay, so what does this tell us? Is I'm going to use periodicity. Now I can look at this point, right? This point, and in the left-hand side is my solution between 0 to a. On the right-hand side is this point. This point is this point, right? Periodicity. And I have solution for this region. I have solution for this region. So I just need to relate through the solution through the block theorem. So at the x equal to a, I use the block theorem. X equal to a, the block theorem say the wave function is related, and also corresponding, you take a derivative, derivative is also related. Okay, so the wave function is a. In the first region, 0 to a, you see we have that solution is a exponential minus I, capital A, Ka, plus b exponential positive Ka, right? And this equal to exponential I k, small k, times t. That's the t equals a plus b. And then times the wave function when x equal to minus b. So if I do x equals minus b in that region, minus b to 0. So when x equal to minus b is say exponential qb plus d exponential minus qb. Right? So I got my third equation, and similarly, if I take a derivative, I got my fourth equation. So this is the wave function block theorem, and derivative block theorem again. So derivative is, if I take derivative, you can say they're equal. So I have IKA and a exponential minus a exponential IKA plus b exponential plus Ka, this is capital, and equals exponential minus IKT, and you have a Q in the front, and minus say exponential QB plus d exponential negative QB. We're not going to do more operation of those four equations. The point I want to make is, if you look at this, it's a homogeneous equation. No constant, right, terms. A, B, C, D, you have four coefficients. And all constant terms, if you move to the one side, all constant is 0. So this is the characteristics of eigenvalue equations. And you are, if you have homogeneous equation, to have a non-zero solution A, B, C, D, your determinant must be 0 for linear equations, right? Everybody's following me? The determinant of 1, 2, 3, 4 is 0. If you say this is determinant 0, you look at this, capital K is a function of energy, right? K is a function of energy, E. And capital Q is a function of energy. So capital Q is a function of energy, right? So given the A, given the B, we know T, and for each K, I have a solution for energy. So this is where my math will end up, right? So because this is a homogeneous equation, my determinant must be 0. The coefficients. You put all your coefficients together, and you will get an equation that allow you to determine the energy levels of the electron in such a periodic potential. Okay. So let me do a few steps of math. And if you do the determinant, you actually will get an equation not that scary. Is a Q squared minus K squared capital, and a 2K Q sinh function, hyperbolic sine QB, and sine, real sine KA, and plus cosine QB, and a cosine capital KA. On the right-hand side is cosine small k, that's a wave vector, A plus B, that's the periodicity T. Okay. So this is the, if you do your determinant of this 4 equation, at the end you get this set of equation, this equation here. In this equation, Q has energy, K has energy, and small k. So for each k value, you can solve for that energy in the equation. Okay? And this still, it's not very graphical. Mathematically, it's still too complicated. So let me make one more simplification for the purpose of explaining this solution will lead to the band gap in the material. The band gap is essential if you think about semiconductors, all those, right? So my next step is I let B goes to 0, but say I will keep U times B, because when that B is 0, this is a very narrow, say B is very low, so this becomes very narrow, right? And U times the B finite. That also means the potential is going to shoot up very high, right? But say with this, if I say B goes to 0, Q times B, this gets to just approximate the QB itself. You linearize it. So this by that the Q cancel. So what I have here, I can write this P capital K times A sine capital K times A, and plus cosine capital K times A equals cosine Ka. Because B is 0, so A itself is the periodicity. This is V vector. This K has energy, and the P itself is just a constant. P here is a constant. Okay, so this one, with this, I can go say graphically what this solution will look like, right? You can say now, the left-hand side is cosine. The maximum is -1 to +1. The right-hand side, I want to find the energy, K, right? In this capital K has energy. Capital K is 2meh². Okay? So you can say this is between -1 to 1. And here is a factor right? When Ka goes to 1, this divide this. Sine x divided by x is 1. So the P plus, so this could be larger than 1. In that case, there's no solution. Right? There's no K, capital K would satisfy that. So graphically, if I do my solution, what it looks like, so what I'm going to draw here on the is as a function of Ka. So here I have K, capital Ka, and because this is a little bit difficult to solve, so here is that function on the left-hand side. On the left-hand side is just eventually decrease into cosine, right? Okay. Yeah. And on the so this is a Ka, and on the right-hand side is the range is -1 to +1. So because I want to find the solution K for that include energy, so this is the range between -1 to +1. I'm not drawing well, so this is a +1, this is -1. So that means when Ka in this region, I have solution. In this region, I have solution. In this region, I have solution. But as Ka becomes larger, eventually this is within -1 to +1. So I have a solution everywhere when this Ka becomes very large. K means, again, energy. So that means when energy is very large, I don't have forbidden region. But in this region, this is my forbidden. I don't have any energy in this region, right? This region, I don't have a solution. Okay? So if I replot this, because what I'm saying here is this region for any Ka, cosine, this small Ka, if you give me a values that cosine small Ka, I have a corresponding energy solution, right? So I can go replot that Ka, because this is a periodic function. So now this is a capital K that gives me energy. My next is I'm going to plot this function in small Ka. Hope you don't get confused. Okay, I'm going to plot what the solution look like. And the solution is, say, because this is a cosine Ka, so it's a periodic. So my solution will look like this. And this is the energy. And essentially what that energy has is derived from K, right? This capital Ka is in this region. That's the solution. And so this is if in this region, and in the next region I don't have energy. This is forbidden, so I can't. For the when in this region of energy here, there's no solution. So there's a gap here, right? Because this is beyond 1. So what I have is next, what it looks like. Okay. So in between is a gap. This is the gap that I've been talking, right? That's the corresponding to this region here. I have no solution, low allowable energy. Electron cannot have this energy when they put in the periodic structure. Okay, so this is my how the solution will look like, and let's leave it here and come back to look at this wave vector. What is the allowable wave vector values, right? So for the wave vector, I have to go back to the here. This is the Bloch theorem, right? And so I need to decide what is the wave vector, and I know I have n atoms in the crystal. So between this 1 and the capital N, the total length of the crystal, right? L, the length of the crystal, is the n atoms times the periodicity, right? And this periodicity in the limit I'm considering is n times A. A is my pure, right? Because B is 0. Okay? So this is where there is a very interesting boundary condition, sort of artificial boundary condition that was introduced. And this boundary condition is, this is a 1, this is an n, right? That's a finite length crystal, right? There is a finite length. And von Karman introduced the periodic boundary condition. Okay, now I'm going to write von Karman. And what they say is, because this n, capital N, is usually very large, it really doesn't matter much. And one way to say a periodic boundary condition is say, after this 1 to n, the crystal repeats itself. So n plus 1 come back to 1. Okay, so what you say, the wave function of n plus 1 equals the wave function of 1, first atom, right? And your real space is going from 1 to n. And this is called the von Karman periodic boundary condition. And what it does tell us is when so what we have here is say when x equals n. So what I have is psi x plus Na, right? That's the say length of the crystal is equals psi x here. Okay, and with that I will have exponential ik times Na should equal to 1. So this is what the von Karman periodic boundary condition gives me. And it gives me a way to say k equals 2 pi Na, that's the length of the crystal, and times small n. And this n is plus minus 1, plus minus 2, and plus minus n. You continue. Okay. Now, what it means is this small k wave vector is not a continuous function. It has, if you look at this n, whenever n equals the length of the crystal, right? Say n equals capital N, and I have the Ka, k times A will repeat 2 pi, right? K, if you look at that small k times A, when n say equals capital N, small n equals capital N, that's 2 pi, right? So here what I have is this is 0, this is 2 pi, And between Ka, between 0 to pi, I have really n points. So I will have the number of points is n points here. N is the number of atoms in the crystal. Okay, I think the other way I want to say this, the von Karman periodic boundary condition really doesn't matter. Basically, I have electrons that extend, the wave function extend between 1 and n, right? I have a wave function in the region of, say, 0 to L. Because, say, this is my beginning. The total L is the total length, right? So now I ask you, if you know a function, whatever function between 0 and L, x equals 0 to L, right? And you know you can do a Fourier series. This is a finite length function, right? If you go recall your Fourier series, if you have a function between 0 to L, you write into Fourier series sum. What is it? Huh? Cosine x, right? Any function between 0 to L, you can decompose into the series of sine and cosine functions. Okay, so let's write that. So I have, in general, any function, I can always write A0 plus sigma n equals 1 to infinite, right? An cosine 2 pi n over Lx, and plus Bn sine 2 pi n Lx. Right? That's any function. As long as, say, I know this function between 0 to L, I can expand it in sine and cosine series. You agree? So what does this tell me? If I write sine cosine in exponential, is say let's say an complex and exponential I 2 pi n L x plus Bn complex and exponential minus I 2 pi n L x, right? I can rearrange and write it into exponential. Once I write it into exponential, what does this mean is this is the stationary part of the Schrodinger equation, right? You remember there's time-dependent exponential minus I omega t. If I put a minus I omega t into this, multiply together, this is a wave propagating to the positive x direction. This is a wave propagating to the negative x direction, right? So I'm decomposing this wave function into many modes, right? Again, the modes, right? 2 pi nl, each n is one wave, one wavelength. Okay, so I'm decomposing this into many modes, and so what I have is every 2 pi I will have a total of capital N points. Okay, and it's very important to understand this counting. So basically, even though this function I'm drawing is continuous, and I have many very closely spaced points as wave vectors, and the total between 0 to pi, say Ka, 0 to pi, is a capital N point states. Okay, so this is the representation in terms of, because it's periodic, so now I have the option, because I don't want to draw all this. So I can take a 0 to 2 pi, I can draw this. That's enough, right? But say, even this is not the usual way to draw the band structure. And in fact, say, people don't like to draw 0 to pi. They like to draw 0 to pi and 0 to negative pi. Any 2 pi is fine, right? So I can draw really between here and forget the rest. And that's 1. And even this from negative pi to positive pi, again, there are endpoints, right? 0 to pi, there are endpoints. Negative pi to pi, there are also endpoints. But say, it's symmetric, right? The wave going forward, positive x direction, negative x direction, they are symmetric, right? That's why my solution, positive k, negative k, is symmetric. So because of that, I only draw half, so 0 to pi. So that's usually what you will say when people plot the band structure. And this, say, what they'll say is they don't plot Ka, they will plot here 0 to pi, so it's pi over a, that's a k, wave vector. And here is the energy, and this is the solution for whatever potential in this specific periodicity direction of the crystal. Right? I say it's a 1D crystal, right? In real crystal, is every direction you look, you can say, okay, I'm consider the periodicity in that specific direction, and that's my wave vector. That's why now it's a vector. Wave vector direction is along that specific direction of the crystal. And we'll discuss in the next lecture more on the crystal, geometries, different geometry of crystal. Okay, remember here, because it's 0 to pi only, so there are really a half n, right? N over 2 points between 0 to pi over a, because there another half is between on the other side. Right, negative side, which I didn't draw. Okay, so what's so special out of those? Those are the electron energy level, and this is so you have this say semi-continuous curve. The curve itself you draw continuous, but because k is discontinuous, this n is also really close spaced but discontinuous point. Right. What's the relation between what we talked of atomic orbital at the beginning? And roughly this band is n equals 1, right? If I think about the hydrogen atoms, negative 13.6 n squared, right? This band is n equals 1, this is n equals 2. Now it's split into many small levels, right? And we see at the beginning when we discuss hydrogen, if I have n atoms, I have n energy levels. Now I have n points between negative pi over a to plus pi over a. So I have n energy level in each of this band. Okay, so physically it's a different picture, different views, but they are all the same thing. Now a few more discussion point. And first, we discuss this small k wave vector. One is this in a crystal h bar k, right? Remember, the wave particle duality is h over lambda is right h bar over k times k, and this is called in crystal is called the crystal momentum. And without going into detail, we can. This is the momentum when you think about doing the energy conservation, momentum conservation. Right? When two electrons scatter with each other, they still have to obey energy conservation, and they still have to obey the momentum conservation. And you see, this is the momentum that we'll be using. And in 3D, K is a vector, depends on different crystallographic directions. And also, we said that before this, say K and K plus pi over A are equivalent. That's why we reduce this periodic representation into only between negative pi over A to plus pi over A. And what's really striking is the gap, right? From this, we see there, you see this region, there's no energy. There's no electron in the crystal can have those energy. And here, similarly, there's no electron in the crystal can have those energy, right? So we have an energy gap. Okay, and it turns out that, say, in real crystals, we have many different directions. So maybe in one direction is this way. Maybe in another direction, the potential is different, right? The periodicity, this is pi over A1, periodicity in that direction. And maybe in the other direction is pi over A2. So it's not when I draw this, I'm drawing the other direction. It's not the negative. I'm just drawing the other direction. Okay? And it might be even having possibility of this way. Okay? And but say in some material, it turns out that there is a gap, no matter what. Consider all directions, there's an absolute region where there's no energy. And this is the band gap of the material. Okay? So energy gap and the extension is 3D is a band gap. Okay. Now, let's do a little bit counting and to say what does this mean. So I take my hydrogen, one-dimensional hydrogen chain as example, right? I put the electron. So if I have a hydrogen chain, one-dimensional hydrogen chain, that's here, right? And I have not added spin. Now I have to add spin. Right? Spin is afterthought because my solution doesn't include it, right? So each energy level, in fact, is S plus and minus, right? S 1/2 minus 1/2. So there are two quantum states. Now, I put the electron always anything except the humans, right? Like to go sit in the lower energy state, right? And well, biological system may not. Say humans, say. So I put the electron, they go to a lower energy state, right? And if it's hydrogen, so there are n electrons. Each hydrogen has one electron, right? Between negative pi over A to plus pi over A, I have n points, and that means I have 2n because the spin, I have 2n quantum state. So Pauli exclusion say each quantum state has maximum 1 electron. And also the minimum energy principle, thermodynamics say, right? I haven't brought in the temperature, but thermodynamics say the electron goes to lowest energy first. So what happens is, okay, now I have electron, go here, go here, go here, and fill in here, right? Because it's half. I have 2n state, I have n electrons. Right? So where electron fill to the top, I say is this point is the Fermi surface, Fermi energy, Fermi level. Okay, so we have Fermi level. This is a EF. Okay? And now, in this simple picture, electron fell to the half. And now, if the temperature is not 0, electron get a kT energy, right? Electron, and the kT energy, those electrons maybe way below kT, they don't move. Those electrons near the Fermi surface, they have energy kT, and the energy separation between these discrete small levels are small enough, so the thermal energy can make them move to other states, right? So electron can move in the band. So those are metals, right? In metal, the Fermi level falls into the bands. And in metal, not every electron will be contributing to the conduction.
What is so special about Fermi?
Fermi level is just a concept that will say if I fill in where is the topmost. You fill in level in the bucket, where is that surface there? That's where they say those. So only electron near the Fermi level have a kT energy that they can move around. Electron way below the Fermi level, right? kT, the other states is a field. The Pauli exclusion principle say no way, I don't allow you there. So the electrons in this region, they don't contribute. So even in metal, you say you're going to take a copper, take a lattice constant, you say per unit volume how many electrons. But not all those electrons will move, will contribute to conduction. Only the ones near the Fermi surface. Okay?
The Fermi surface has to be the lowest band?
No. I take the hydrogen example. Now I'm going to take a helium. Okay. Now what happens if I do helium? Where is it? So this is going to be here. Helium has 2 electrons, right? So I have 2 n states. I will fill to this region here, right? What happened? And that depends on the gap here now. kT is 26 milli-electron volts, right? 26 milli-electron volts. And if the gap is a few electron volts, 5 electron volts, right? So they are all filled, and the kT cannot lift the electron to here. There is a real forbidden region. Your electron cannot have that energy. So now you have a gap. And this is the, in that case, if the gap is really large, let's say 5 electron volts, it's an insulator. It's a dielectric. It's an insulator. You look at glass, right? The glass is an insulator because there is a really large gap, energy gap. So photons, visible photon is a 0.5 micron, right? 1 micron is 1.24. I can't remember which is which. 1 electron is 1.24 micron, or the half. Well, it's 0.5 micron is about 2 some electron volts. Okay. 2 electron volts. The gap is much larger, so the light will transmit through the window. They can't lock the electron from here to here. They don't have enough energy. Yes?
For semiconductors, where the Fermi levels
Okay.
in the mid gap.
Okay, that's you're jumping.
Oh, sorry.
Good question. I'm not so I have to go to more talk about semiconductor. Right? So semiconductor gap is typically about 1 to 2 electron volts. Okay, and in that case, there's some of the thermal energy, even though it's 26 milli-electron volts. I have not talked about the I mentioned Boltzmann factor, right? So there's a distribution of that energy, thermal energy. Some electrons have enough thermal energy, very few, they can jump, right? If they have enough energy thermally, they can be locked from here to here. So what happens, okay, I'm talking about, that's a 1D example, right? Here 3D is the same, I have a gap, right? So some electron can be locked from here to here because if those electrons have enough high energy compared to the gap. So what's going to leave behind if I have, okay, so one more step. 1, 2, helium, right? Go to the next one, lithium. 3 electron. It has to go to the here, right? The next band. And so the Fermi level don't have to be lowest one. It's just you have to feel, you look at the periodic table, you feel to the topmost. There are many bands. Okay. And so when we have the, let's say I'll take the simpler one. It turns out sometimes this is the lowest, this is the highest. Depends on, this is a K. This is where I draw K. I'm drawing a small region. I can be drawing here or I can be drawing here, okay? So now this is my band gap. This is EG. Silicon EG, what is silicon EG? 1.1, 1.12 electron volts. What's the gallium arsenide?
0.46.
1.4, okay? So now I have some thermal energy, so what happens is some electron, very few normally, will be locked from lower energy to higher energy, right? So what left behind is some empty states. So now I have some empty states. And I have some filled states. This is the conduction band, this is the valence band. Okay, conduction band, valence band. Valence band has some empty states. And electrons now suddenly in this band, again, because the energy is so close to each other, those electrons can move around, right? And these electrons feel to the top. Now, originally, if it's at 0 temperature, they feel here. They can't move, right? But now at some temperature, room temperature, there's some empty states left behind. So these electrons, now they can move around those empty states. Most of those electrons here, sitting here, they don't move, right? So it's a one stone, two birds. Electron move from here to here. Electron can move here. The empty states also make the rest electron happier. When your lab is too crowded, that's the situation, right? The guys move into bigger room happy, and the guys left behind also happy. That's what happens to a lab. And so those empty states, it's better than rather than majority of the electron move into empty states. The opposite is those holes. So it's a positive charge. So there's no hole, okay? It's just a charge. It's easier to describe those empty states as a holes. And this is the electron. So we have valence band, conduction band, and valence band. And this is the valence. So you can say that you have to really go to quantum to understand even the basic why there is insulator, why there is a conductor, why there is a metal. Okay? And now I thought that I'm debating whether I show the slide, go to do a weekly exercise, going to the website or going to continue. But then let me just, because I think I need to finish this, so I'm going to skip that. This is the intrinsic semiconductor. There's always equal number of electrons and holes, right? Because the one electron go up, leave behind the hole, empty state. Now, most of the time you don't work with just intrinsic. You actually put dopant, right? So what do? You put in silicon, right? If you look at silicon, it has 4 electrons. You put a phosphor, so silicon as a periodic structure, right? 4 electrons, they're all happy. Now, rather than silicon, you put a phosphor here, it has 5, right? The extra electron can detach from phosphor and become commonly shared. And so basically the energy level of the phosphor is somewhere here. The thermal energy is so high, is enough to lift this electron from phosphor to the conduction band. So in that case, you dope it. That's called doping, right? You artificially put the dopant. You put the phosphor, that's the N-type. You put the boron, which has 3 electrons. What that does, so it turns out boron energy level is here. And then say the electron is so happy to say a close energy level. Say once, so you will fall here. You say KT, right? So leave behind empty state. So you have holes. So you dope, you boron, you dope, you get a say holes, right? P-type. You dope phosphor, you get N-type, right? So that's the semiconductor. That's extrinsic. So we have the difference between extrinsic, that's a doping, and the intrinsic is when you don't dope it, right? And intrinsic, in fact, sometimes it's hard to make. When you purify silicon, you can't make that pure. And gallium arsenide could have semi-insulating substrate when you buy it. That's because the gallium arsenide band gap is 1.4, is higher than 1.1. And so there's very few electrons intrinsically if you try to purify, even though you still have some impurities. Okay, there's another big difference. Here, when I draw here between here and here, right? If the gap is happen in different direction, right? You have to look at different direction. I'm going to talk more of this directionality. If this is not at the same point, this is the momentum, K momentum here, electron, whole momentum, electron is here. It goes there. You need a different momentum, right? There's a change. So that's an indirect semiconductor. Silicon is an indirect semiconductor. And a lot of cases, it turns out also the minimum and maximum is the same place. That's a direct gap semiconductor. Gallium arsenide is direct gap. So it turns out the light doesn't have much momentum. If you think about them, say H over lambda, lambda for light is half micron. For crystal, A is lattice constant, is an angstrom, right? So photon momentum is very small. So, but say when it's a direct gap, it can easily excite because the momentum conservation is easier because vertical transition, no momentum needed. But in silicon, that's not easy because it's going from here to here. It needs that momentum. So it's an indirect semiconductor. And that's why the light source, lasers, are made of gallium arsenide. But say always people want to say, can I make a light source with silicon because silicon is so good for electronics. It's not good for optics, right? And that's also a reason why silicon doesn't absorb well. So when you make a solar cell, you have to make it very thick because say the chance of light again when it gets into the crystal get absorbed is not good. So you make it thicker to increase that chance. Okay, yes?
How do you decide which one? I mean, for hydrogen, for example, where is the valence band and conduction band when you here?
Hydrogen, this is my simple 1D picture. This is here, so it's a metal. I don't even call it the valence of conduction. It's a metal, right? This is my conduction band, right? And helium here, right? Then if electron go from here, then this is valence, this is conduction.
Highest occupied
highest occupied, yeah. In fact, when you do molecule, this is called highest occupied molecular orbital. So when you do, say, plastic solar cells, there people talk about HOMO and LUMO because the wave function is, the wave vector is, the energy is no longer discontinuous. It's sort of discrete. Then your language actually was official. HOMO and LUMO, highest occupied, highest unoccupied, lowest unoccupied. Okay. I'll make up for this slide, say looking at the journals next week.